Right, okay, so here we go. So last time we were just kind of starting to talk about Green's theorem. We didn't actually even get to Green's theorem. It takes a while to get to Green's theorem. I have to build up certain ideas and context and points of view. So just a quick reminder of what we did last time. We talked about boundaries, kind of a new point of view on boundaries. Don't forget, going forward, boundaries are now oriented things. The word boundary itself, whenever you hear that word in chapter 6 and 7, that means that they're talking about an oriented thing, and you have to know what the orientation is, and the orientation is implicit. It is following this convention that we talked about last time. Okay. All right. Next thing we talked about is the idea of an accumulating quantity. We've seen a bazillion accumulating quantities, all of single variable calculus. When you compute something with an integral, that quantity is an accumulating quantity. That's what integrals do, is they compute the whole as the sum of the parts, right? And that's what an accumulating quantity is. Any sort of a quantity distributed over, in this case, appropriate to our context, distributed over an area, such that if you cut the area into two pieces, the quantity of the whole is equal to the sum of the quantities of those individual pieces. So, for example, mass is an obvious accumulating quantity. The whole is the sum of the parts. But then perimeter is pretty easily seen not to be an accumulating quantity. Okay, we talked about those details last time. So then I make this eyebrow-raising proposition that boundary circulation is actually an accumulating quantity. Specifically, boundary circulation accumulates over areas, in the sense that if you think about the boundary circulation for the whole here, right, and then if you also think about the boundary circulation on the left piece and the boundary circulation on the right piece, the whole is the sum of the parts. Boundary circulation works. Now, it feels like it shouldn't because, again, of these two sort of interior pieces, and you feel like that, well, yeah, but when you're looking at the sum of the parts, you get that line integral and you also get this line integral, and those are not parts of the boundary circulation of the whole. So there you go. There's the difference between the whole and the sum of the parts. And then, of course, the retort is that, yeah, but these cancel, because they have opposite orientations on the exact same curve. So having canceled, then indeed the whole is the sum of the parts. So it's a little bit of a weird thing that even though we compute boundary circulations on the boundary, as it says, it's right there in the name, right? Boundary circulation. You think of it as being on the boundary. I'm going to encourage you to try not to think of it as something that's on the boundary. Think of it as something that is distributed over the interior. Kind of like mass would be distributed over the interior. And the reason I want you to think of it that way is because it behaves just like it's distributed over the interior. Right? Because again, if you chop it in half, the whole is the sum of the parts, just like mass would be. Just like any quantity that's distributed over the interior. Okay. And so, just as a related for example, and this is where we ended last time, feels like a weird, nonsensical question if I were to ask how much of that boundary circulation happens here. It's tempting to say, oh, those are entirely different curves. Those curves don't even touch. What do you mean some of the purple is happening on the green? It seems nonsensical. But again, if you take this point of view, and I know it sounds weird, but if you take this point of view that the purple circulation is actually distributed across this purple interior, right? And then if I ask how much of this purple accumulating quantity is there in this region? Well, now all of a sudden it becomes a perfectly sensible question. How much of the quantity distributed over the area over the purple area. How much of it is in the green area? Okay, a perfectly reasonable question. There's nothing odd about that at all. So again, kind of a weird point of view, but that's the point of view that we're going to push, because that's the point of view that allows us to write down a really awesome theorem momentarily. Okay, so again, even though this is an abstract kind of, you don't think of it as being stuff, we are going to think of it as being stuff. How are we doing on that? Is everybody okay? Willing to follow along on that? Yeah, question.
So this is a little bit farther back, but
okay.
I don't understand how perimeter doesn't accumulate over an area.
Yeah, okay. So let's think about this region right here, and looking at the whole. I'm going to draw a picture of the perimeter. There's the perimeter of the whole. Okay, now let's think about this left half, D1. I'm going to draw a picture of its perimeter. That's that right there. That's the perimeter of the left half. And then likewise, here's the perimeter of the right half. And now I'm just going to ask, is in the spirit of is the whole the sum of the parts, I'm going to ask, is the purple distance the same as the green distance plus the blue distance? And
it's not because of the piece that intersects.
Yeah, it's because of this these sort of two extra pieces of perimeter that you get when you make that slice, right? And so there's just simply more perimeter on the two individual pieces than there is on the whole itself. Does that make sense? We could literally compute that perimeter.
Right, yeah.
That perimeter is equal to this plus this. Yeah? But yes? What we had in purple is the same as this plus this. So therefore it's not equal to this plus that plus this. Right? All this extra stuff I added in, it just makes those two things just not the same. Does that help?
Okay. Because
yeah.
Would it be fair to say that it doesn't add up to? It does get larger as you increase area, but not at a proportional rate.
I don't know what that means.
Okay.
Yeah, the question is just, are they equal or are they not equal? And how they're not equal, the stuff that doesn't have this key property of accumulation is stuff that we just don't care about in this context, right? And so studying the stuff that we don't care about is we don't need to go down that path. You understand the motivation there. We just have no incentive to, right? So what we're interested in is the fact that this quantity does accumulate. So we want to understand accumulating things.
And those accumulate because there's cancellation between the two going on.
Yes. That's exactly right. Because of the fact that, even though it kind of feels like there's going to be, look at this here. This is part of the sum of the parts. That's not this is not the whole, but it is in the sum of the parts, and it seems like we've got a contradiction. It seems like we've got a difference, but these cancel. And, so there is no difference. All good?
All good.
Okay. Cool. Okay, so moving along. So if we've got a stuff, and again, I know it sounds weird, but boundary circulation is a kind of a stuff. We're thinking of it as a stuff. Well, then we can talk about stuff per unit size. Right? Now, just as a quick reminder, when we're talking about mass density, in a given region, we can talk about how much mass there is in that region. Right? And taking that mass and dividing by the area. Right? Well, mass divided by area gives you what we call mass density. And now, a lot of people will just call this density, and that's fine, I suppose, just call it density. If there's only over one density you ever talk about, then you don't need to clarify what kind of density it is. And in a lot of high school physics classes, mass density is the only kind of density ever discussed. But we're going to clarify this as being mass density, because mass is the kind of stuff whose density we're talking about. So now, just following that pattern, this linguistic pattern of how we're using the words. I mean, we can just as well talk about this different accumulating quantity called circulation. Again, that's an accumulating quantity. I can talk about how much boundary circulation there is, in that piece. Now, of course, it's not, we're thinking of it as being in that piece. It's actually measured as a computation that goes around the boundary. Yeah, sure, but we're not going to think of it that way. We have an accumulating stuff, and I can talk just as well about how much stuff there is per unit area. Same deal. And in the same way that the above is called mass density, I think it's very believable that what we have here is going to be called circulation density. Totally analogous to the idea of mass density. And this is a really important concept, this idea that we can not only view circulation as being an accumulating quantity, but that we can therefore view it as having locations, and therefore we can talk about an associated notion of density. Everybody with me? All right, we're a hop, skip, and a jump away from being done with stating and motivating Green's theorem. I just need a little bit of notation to work with before we do this. And so, keep in mind there is a vector field in play when you're talking about circulation. Circulation is something that's measured with respect to a given vector field. So let's suppose we have a given vector field. Here's the formula for circulation density. In other words, for this thing right here, circulation per unit area, it is computed by that formula right there. Now, why? Where does this formula come from? There's some details we could write down. It's not that hard even. It's in the book. You can read that if you're interested. I find that, though, to be nitty-gritty. It's details that ultimately are just computation. And I don't think it's particularly an illuminating. I don't think you'll leave this course with a better understanding of what's really going on from having followed those details. Not particularly anyway, maybe a little bit. So far more important than where this comes from is what it is and how to think about it. This formula is, and this is really important, is telling you how much circulation per unit area. It's stuff per unit size. It is density. That's what's really important to take away about this, yes?
Just out of curiosity, does that connect to, it kind of looks like something you get from a cross product?
Yeah, I hear you. Yeah, there is a connection of sorts. Yeah, we'll get to that in a minute. Yeah. Okay, so there's the formula for circulation density. I like to refer to this as Green's operator because this is going to be the trick operator that makes Green's theorem work. So Green's operator seems like a reasonable choice. I like to abbreviate it, being as I'm calling it Green's operator, I like to abbreviate it as GRN. I don't know. It's possible I made that up. It's possible I'm copying something I saw so long ago I can't place it. I'm not sure. But I like this notation. I've used this a lot. Also a very common notation, rot. That's short for rotation. And recall what circulation is in the first place. Circulation, right, is measuring the extent to which the fluid goes around this boundary along with the curve. Namely, it is measuring, in a sense, how much the fluid is kind of rotating. Right? Now there's kind of a stirring of the liquid there, of the fluid. And so rotation is a pretty reasonable term to connect to this operator. So very common choice, and again, I'm a fan. I think it's very reasonable. It is also sometimes called curl. I have my problems with this term. Not that there's anything really wrong with calling it curl, but my problem is that there's a three-dimensional version of this called curl, which algebraically is pretty different. And it just gives me the willies when we use the same term to refer to two pretty different things. Now, they're closely connected and related. Yeah, sure. still, to me, they're algebraically different enough that I don't like using the same name. So I'm going to prefer not to call this thing curl. But I want y'all to be aware of it because y'all will hear other people call this curl. So heads up, this is what you might call a two-dimensional version of curl. So, kind of. So let's see here. Let me circle this one in orange. It's not wrong, but I'm just not excited about it. This one is actually pretty awkward. Our textbook uses this at least once. What I don't like about this, and so you asked about curl or about cross product, and here it is, right? You can see there's a cross product in this notation right here. The problem is that in order to make sense of this as a cross product, we need for this vector field to be a three-dimensional vector field. It's not. Yeah. Right? So this is, I don't much care for it. Now, if you were to append a 0 and make this a three-dimensional vector field and then compute the curl of that and then do a dot product with 0, 0, 1. Yeah, then you get this formula. Right? So, I guess. But then my response is, okay, well, yeah, but what's with the urge to use this weird notation that's so much harder to write down than any of these others? Right? And it's not even... I just find it awkward. So you'll never catch me writing this notation other than to explain why I'm never going to write this notation. Right? So anyway, it's there. Be aware of it, but not a fan. Okay, so we've got all of our tools. We're ready. We're in business at this point. We've got this idea of oriented boundaries. We've got this idea of accumulating quantities. Boundary circulation is such a thing. Boundary circulation is an accumulating quantity. Boundary circulation is distributed across interiors like a stuff. And has an associated density like a stuff. And now let's just kind of put the pieces together. We're basically there, believe it or not. But so here we go. Circulation. I'm going to view circulation as being a quantity that I can associate to an area. Got a notation for it, right? Sigma, lowercase Greek letter sigma. We've observed that circulation is an accumulating quantity. The whole is the sum of the parts. So in the same way that if I say, what's the total mass? Well, it's a sum of a bunch of little pieces of mass. Well, likewise, circulation is the sum of a bunch of pieces of circulation. And then we have this idea of a corresponding density. Namely, if I want to talk about how much of circulation is there in a little piece of area, this density, stuff per unit area, is what you multiply by area to get stuff. So we've got these kind of arguably just two big ticket ideas that this concept, this quantity called circulation accumulates, and that there is this associated notion of a density. And check it out what our theorem has turned into then. This is really a pretty remarkable theorem. We have that this vector line integral can be computed with a double integral over the interior of this thing called Green's operator. So we're going to compute, believe it or not, a line integral with a double integral. Really hard to see that coming, right? But nevertheless, immediate result from these ideas of accumulation and density that we talked about. Yeah?
What is the subscript in the first integral?
Oh, yeah, I'm sorry. I should have hit that when we were talking about boundary. So this symbol here means boundary. And I know it's exactly the same as the partial symbol, and it's just a kind of arbitrary alternative usage of that symbol. Yeah, I mean, there's a sort of a hand wavy justification, a motivation for why we'd want to. It's not worth talking about. Anyway, just going forward, that means boundary. Yeah. All right. So yeah, weird that there's a theorem, but it's true. All right. Okay, let's see an example. We want to compute a line integral. We are given this vector field, and we have this domain. Keep in mind, this being a vector line integral, the domain needs to be an oriented curve. Notice that my curve is oriented. This says the clockwise oriented unit circle. All right, everybody good? Okie dokie. So how are we going to compute this integral? Let's take a quick moment to recognize that if I were to brute force this, I can parameterize the unit circle totally. Right? X is cosine t, y is sine t. But here's the problem. If x is cosine t, and if y is sine t, then I'm going to have some pretty ugly expressions in this vector field when I do that plugging in. And so this integral is going to get weird, right? If we brute force it. So hopefully there's another way around this. All right, now, so I'm tempted to say, hey, let's use Green's theorem. Check it out. Green's theorem says you can turn a line integral into a double integral. Who knows? Maybe this double integral might be easier to calculate. Fingers crossed. Let's hope. Here's the problem. This integral, as written, does not qualify. Now, you got to be really careful when you're using Green's theorem, and there's other theorems that kind of behave a lot like Green's theorem. Really, really careful. If you're going to turn a line integral into a double integral, notice there is a restriction. It's written right here on the page. It's looking at us right now. A lot of students forget about it. This is a very, very important condition. The condition is it has to be a boundary. Green's theorem does not apply to just any random line integral. Green's theorem only applies if the domain is a boundary, and a boundary is a trick word. Don't forget, boundary means not only oriented, but oriented a certain way. So we have to check and see if we're going to use Green's theorem. Is my curve a boundary, strictly speaking? And, well, the clockwise oriented unit circle is this right there, and the region is not on my left. This is not a boundary. Green's theorem does not apply. We're out of business in terms of immediately applying Green's theorem here. Does everybody see that? I'm sorry that this is the case, but it's really got to be a boundary, and strictly speaking. Okay, now there is a hack fix for this. The hack fix is to recall that I can talk about the same curve with the opposite orientation, C minus, and wait a second, C minus, as I cruise along C minus, the region is on my left. And it does go all the way around. C minus is a boundary. So C minus I can actually do something about, right? C minus is literally the boundary of this disk here. So let me do it like this. So C minus is the boundary of that disk D. Everybody on board? So there's kind of a two-step process then that I can do to make this fit into Green's theorem. First step is to recognize that my curve, let's see, how am I going to do this? Here we go. Just with an opposite orientation, right? I can replace C with C minus. And then secondly, C minus, being as it is a boundary, I can rewrite the integral over C minus as literally an integral over a boundary. Everybody on board? Okay. And so, all right, well now we're in business. We are off and running because now don't forget your minus sign. It is easy to forget that minus sign, but that does have to come along directly. Then I can say, oh, boundary circulation. Cool. Green's theorem tells me boundary circulations are computed as double integrals over the interior of Green's operator, whatever that is. So here's where we use Green's theorem. Everybody happy? Let me remind you, I mentioned something along these lines last time, but don't make the mistake of being under-impressed with the importance of the orientations. Orientation is a sophisticated, important, substantial idea here, right? And even though it only amounts to a minus sign, it's not about the answer. It's not about, oh yeah, it's just a sign error. That's just not what it is. Remember, it's about the reasoning and what your work demonstrates about your proficiency with the relevant reasoning to solving a given problem. And orientation is important here. It's a significant, important idea. So this business about switching to the opposite orientation, this business here, would be a significant number of points on an exam question about this stuff. So please be very, very careful and thoughtful about orientations. Yes.
Does the boundary need to be closed?
Yes. So it still has to be a boundary, right? It still has to be, and I recognize we've never quite defined what we mean by it. It still has to be a fence that will keep the sheep in, right? So yeah, it does have to close up. Yep. Absolutely. Okay. Yep.
I'm still a little confused about how we got to C, negative C is equal to partial D.
How we got that? This right here?
Yes.
Oh yeah. Okay. So so here's our original C, right? And now here's C minus. But now wait a second. Let me. I was just highlighting sort of casually. C minus actually does go all the way around. It is the full unit circle. It's just oriented the opposite direction.
Okay.
Right? And so there's the actual full picture of C minus, and it is exactly the boundary of that yellow solid disk.
So the only reason that we couldn't use the original integral is because the boundary was oriented in the wrong direction.
Correct.
Okay.
Yeah,
So
but that's a big. I mean,
Right,
yeah,
it is,
it's not. Yeah, that's right. Yeah.
It is.
Yeah.
It changes the entire problem.
Yeah.
By a factor of -1.
Yes, that's right. That's right. Yeah. All right. So next example. I'm sorry. Almost done with this example. So we've successfully turned the meat of the matter anyway into the computation of a double integral. Wait a minute. Double integral of what? Well, it's got to be Green's operator. So we're going to take this vector field. Right, and I've got to compute Green's operator of it. I claim that arithmetic works out like so. Now, keep in mind, Green's operator, we have a formula for it. It's the, let's see here, it's the x partial, let's be careful about this, it's the x partial of the second coordinate, right, minus the y partial of the first coordinate. Casually, we say dq dx minus dp dy. But anyway, x partial of the second coordinate minus y partial of the first coordinate. So we can do that computation here. Let's see here. The x partial of this is 3. And then we're going to say minus the y partial of this first coordinate, which of course is just 1. And so look at that, the integrand, right? Green's operator, this new integrand for my double integral is just 2. So super easy integrand. Now we got lucky there, right? There is no promise that when you take an ugly when you take an ugly vector field, right? There is no promise that Green's operator will just magically be nice. Wouldn't that be good? It's not. We got lucky in this case. It happened to be that it worked out that Green's operator was nice. Sometimes it will be, sometimes it won't be. What it always is something that you can try. It's something, it gives us hope, right? There's the possibility that it might be nicer. If it's not, then we abandon the whole approach and try something else. But there's a possibility this might be useful. And as it was here. Okay. All right, let's see another example. This is a weird one. Our curve here is made up of what I'm going to call 4 line segments, like so. I'm going to reinterpret these 4 line segments as being that plus this plus this plus that plus that plus that. That's the same thing. I just kind of, dramatic pause in a couple of when I get to this point, right? But it's the same pieces of curve all going the same direction, and so yeah. Okay. All right. So now let's look first at what we have there. Good news. That's a boundary. That's exactly the boundary of this region. Let's see here. I'll use green here. It's the boundary of this region D1. Orientation and everything. It's good, right? Now, sadly, this other one is not exactly, this is not exactly the same as the boundary of D2. After all, the boundary of D2 goes the other direction. The boundary, let's see, color choices. Let's try orange. The boundary of D2 is like that. The boundary of D2 is exactly the opposite of these remaining 3 pieces, this dark blue that I have there. Right? So, boundary of D2 is this. Let me do it like this. Boundary of D2 is that. What I actually have is the opposite orientation. The boundary of D2, yeah.
You have it drawn here the correct way, right?
The boundary, I think everything's correct. The boundary of D2 is counterclockwise. The dark blue, the sort of the right half part of C is going clockwise. And
the picture is drawn with the changes that are outlined in that new C equation.
I don't understand. So what I've got circled in dark blue here, what I've got circled in dark blue is what I've got highlighted over here in dark blue. These are the pieces of the C curve. And I'm just saying that those 3 pieces of C curve are the opposite orientation of the orange, what I have in orange, which is literally the boundary.
Okay.
Yeah. Okay. Okay, so now is this curve a boundary? Well, I mean, kind of not awkward. I mean, yeah, it keeps all the sheep in, right? But there's this issue with orientation that we've got to be mindful about. So what I'm going to do is take the integral that I was asked to compute here, right? And I'm going to break it up into 2 chunks. I'm going to break it up into, there's this chunk here. That chunk there, and then there's this chunk here, right? And I'm just going to sort of, separate those 2 parts out because I'm going to be treating those parts differently because of how they're geometrically different. So, no problem. This opposite orientation business just amounts to a minus sign in the evaluation of the integral. And now I literally have 2 boundary circulations. Right? And Green's theorem tells me that this first boundary circulation is that double integral. Green's theorem tells me that this second boundary circulation is that double integral. And of course, don't forget your minus sign, right? The minus sign persists. So don't forget that minus. Everybody on board? Cool. Not much to it here. Let's see. Let me zoom out, and we'll notice that here's our vector field, of which we need to compute Green's operator. right? And again, there's a little bit of algebra. dq dx, so I need to take the x partial of that, which is 5. Then I need to subtract the y partial of that, which is minus 4. 5 minus 4 gives me 9. And these are easy integrals. These are just integrals computed over these nice little geometrically convenient triangles. And what a convenient coincidence! They happen to have the same area, and so blah blah geometry. Answer is 0. Everybody with me? All right. Okay, so it's a pretty neat tool. Green's theorem allows you to compute line integrals with double integrals. Sometimes, cleverly applied, you can use it in the opposite direction. And this is a nice example of it working in the opposite direction. A little bit of a weird application, but let's start with Green's theorem. Here it is. Here's Green's theorem. You'll notice I'm applying Green's theorem just to this one special vector field. It's not a unique vector field, but it is a nice vector field in a certain sense. I'll reveal why I like it and why it's nice in a minute. But for the moment, all that is a statement of Green's theorem. Now, real quick, just as a notational thing, I've stated before that I don't really like coordinate line integral notation so much because it's usually bulkier. But this is a rare instance where it's actually slightly easier to use coordinate notation, right? So, it's convenient sometimes, and this is one of those times. So that's just a notational thing. Now here's why I like this orange vector field. If you compute Green's operator of this orange vector field is 1. Now again, that's not unique. There are other vector fields that do this, but I think this is the easiest vector field that has this property, where Green's operator is 1. So anyway, I like it for that purpose. And what is this bias? Well, this turns my double integral into a special double integral. I mean, double integral of 1, that literally just gives you area. Right? Double integral of 1 is area. So altogether then, this is a little bit of a weird result, but altogether what we have is a theorem that goes this way. If you want to compute the area of some region, one way you can do that is you can compute this line integral around its boundary. And that line integral will compute the area that it encloses. And now you might think to yourself, you know what, thanks, but no thanks. I like, if I need to compute area, I'll use geometry, right? So consider the following. How would you compute the area of this polygon here? Right, that's a pretty nasty little geometry problem. And it's, I suppose it's not impossible. And I could take this and I could break it up into chunks like this, I guess. I don't know, something like that. And what's that? 1, 2, 3, 4, 5, 6. That's 7 triangles. The problem is these triangles are not right triangles. And so computing their areas is going to be tricky, right? This is not an easy geometry problem. Okay, so how else might we compute this area? I'm going to use this line integral, and I'm going to introduce now, before I do another neat fact, and this is another sort of special case. So what I'm about to show you applies only if you're talking about straight line segments. That's it, straight line segments. And in that case, straight line segments are actually pretty easy to work with. You can just straight up parameterize a line segment. That's just a matter of doing it. And you can then literally plug in x, y prime dt into that parameterization, and what you find is when you do the algebra and kind of collect terms and rewrite, there's this really handy little result that on a straight line integral, on a straight line segment, this line integral is computed by this easy formula. That's the average value of x times the change in y. It's a lovely little result. Again, this is only for straight line segments, but it's super easy on those straight line segments. So let me show you now. Let's put these pieces together then. If I want to compute an area, I'm going to do it by looking at the boundary circulation. That boundary circulation, I'm going to view the boundary as being made up of straight line segments, on each of which I'm going to compute like so, and then we're done. So, example, down to this nasty polygon that we were afraid of having to do with, high school geometry. It looks pretty brutal. But let's take these one at a time. Let's look at this first edge right here. That is a straight line segment. And I will compute, let's see here, it starts with x equals 1 and ends with x equals 12. So the average value of x is, what's that, 5.5? No, 6.5, right? 13 halves. That's the average value of x. And then let's see here, the change in y. Well, y goes from 1 up to 6. So the change in y is 5. And so this product, the line integral on that piece, just the product of those, easy arithmetic on that purple piece. Everybody good? All right, and then proceed. You got to go around all the edges, but notice each edge is really easy. Now, I'm going to skip over here to this fourth edge. Importantly, notice that this fourth edge is going somewhat downward-ish, right? It's not going upward-ish. Now, that doesn't make any difference for computing x bar. X bar is, let's see here, the average of 1 and 5, which is 3. That part's pretty easy. Let's see here, the delta y. Here's where you got to be a little bit careful. Delta y. It's not the difference 8 minus 4. It's the change in y. Y starts at 8, it ends at 4. It's 4 minus 8. Right? Y goes down across that piece. So minus 4. So on this dark blue edge here, 3 times minus 4 gives me minus 12. So anyway, super simple arithmetic. And do this for all of the, the whole perimeter. And I went ahead and did the rest of these edges, myself, and now you add up the line integrals in all those pieces. That gives you the total line integral, and grand total then, the area, is just the sum of all those numbers, which ends up being 19. So pretty doable, right? A lot easier than reciting Heron's formula and dealing with weird triangles, the edges of which are going to involve square roots. It'd be a nightmare, right, if you were to break this up into triangles. Way easier. Everybody happy? Okay, moving along. New idea. Flux through a curve. Now, y'all remember the idea of flux. Flux says how much fluid is passing through a surface. Right? Back in chapter 3, we saw flux, and we, imagine there being a flat surface, and we imagine a fluid flowing through it, and we ended up computing total, volume of fluid per unit time. Right, which we distinguish from the velocity, which is distance per unit time. Totally different thing. Okay, so flux through a curve is just a two-dimensional version of the same thing. If you have a fluid that is flowing in the plane, right, you can talk about the amount of fluid per unit time that's passing through a little line segment there. Yeah, cool. Two-dimensional equivalent thing. So instead of thinking about volume per unit time or mass per unit time of water or air or whatever that's flowing through a surface, We might have, again, to think about a migratory pattern of wildebeests or something, and for whatever reason you want to know how many wildebeests per unit time are passing over some arbitrary line on the map. Does that make sense? Okay. Motivated very similarly. Obviously, this should be proportional to the length, because a bigger line means more wildebeests, right? Of course it is, and I think that much is clear. And then it should also relate to not the magnitude of the vector field. That's not the point. The point is, to what extent is the vector field going perpendicular to the, in other words, through the curve, as opposed to along the curve. And so that means I need to know the component of the vector field in the direction perpendicular to the line. Okay, so we end up with this very similar result. Check back to section 3. You'll see we had a very similar looking formula. It just that it was area instead of length. Yes.
Is n a unit vector?
N is a unit vector. Yes, absolutely. Because I need component in order for a component to be a dot product. Yes, absolutely. Yeah. Okay. So now here's a related question. Suppose you have not just a curve, but a boundary. So now I'm going to draw a quick example of a boundary and then point out that I need to focus on just a piece of it. So here is a boundary. That curve there is the boundary of this region. And if I want to talk about the total flux through the entire boundary, what I would need to do is chop the boundary up into little pieces, such as this little piece right there, and try to understand how much flux there is through that little piece of boundary, and then I want to add that up over the entire boundary. So for the moment, I'm going to start off by focusing on just one little piece of the boundary. There's some clever little observations to be made first, and then we'll, as we previously said, we'll add up over the entire boundary. Okay, so here we go. If I've got our region like this. The convention, by the way, when we say boundary flux, there's that word again. Boundary. Boundary always implies an orientation. When you're talking about flux, what we need is a choice of which is the direction through the surface. So what I need is a choice of a normal vector. Do I mean that as the direction through the surface, or might perhaps I mean this as the direction through the surface? So whichever one of these you choose is called the orientation. So when you're talking about flux, boundary means outward. Again, it's an arbitrary convention. Again, it's a standard that's been in place for a very, very long time. And so, again, not optional. Arbitrary, but required. Okay. Right. So, cool. Here's our outward normal vector. And I'm going to make a seemingly irrelevant observation first, and that is that if I have, you know what? Let's see here. Let me use the highlighters. I think this will look better. In fact, okay. All right. So there's my normal vector. Right. If I were to rotate my normal vector, get rid of this. If I were to rotate 90 degrees, I get my tangent vector. How about that? That's the unit tangent vector, and furthermore, it's the correct unit tangent vector, because after all, as I go in that direction, as it should be, the region is on my left. Right? So 90 degrees counterclockwise turns an outward normal into a correct, region on my left tangent vector. And then let me make the other observation that if I take any vector field, whatever my vector field might happen to be, if I rotate that 90 degrees counterclockwise, then I'll get, I'm going to get a different formula here, but this is how you rotate a vector field, P comma Q, 90 degree counterclockwise rotation is negative Q comma P. Now again, that's a Math219 thing. Think back to how rotations work. Rotations are linear transformations. Linear transformations are matrices. Matrices are understood by their columns, right? All of this business, right? So you can work out the details, and this 90 degree counterclockwise rotation can be just straight up written down as a matrix. And that matrix does this. It turns P comma Q into minus Q comma P. So make sure you can do that. If you have any trouble, come to office hours. I'll be very happy to discuss, but make sure you're good. Okay, so now, neat fact. All this stuff that I have in blue, if I were to do a dot product, F dot N, well, the act of rotating both of those vectors 90 degrees counterclockwise, it doesn't change their magnitudes, it doesn't change the angles between them. So this dot product should be the same. So the blue dot product should equal to the green dot product. After all, they're just rotations of each other. Now, why that's going to be useful will evidence itself in a minute. For the moment, let's just proceed with our original calculation. We want to add up all the boundary flux across the entire boundary. Here was the formula for flux through a little piece of curve. It's F dot N times the length of that piece of curve. We're looking at a little length ds. And check it out. Here it is, F dot N. And very conveniently then, isn't it nice that I can replace that with F perp dot T. And the reason that this is nice is because this gets us into the world of the familiar. Look at that guy right there. T ds. Oh my gosh, that's the dx vector. And now all of a sudden this seemingly new kind of integral, a boundary flux integral, whatever that is, right? That we initially wrote down with this formula. We've never seen how to compute those things before. Oh my gosh, do we have to develop a whole new, oh my gosh, that looks hard, right? All of a sudden, hey, no sweat. Now it's just a regular old integral dx vector. It's a regular old, plain old vector line integral. And that's a big win. So what do we do with vector line integrals? Oh, specifically boundary vector line integrals. So boundary circulations. Among many options, we can apply Green's theorem. And Green's theorem says that it's computed then with a double integral. And now it's just a matter of writing down the details. How do you compute Green's operator? Well, Green's operator is this. You do have to be careful here, a little bit careful. We're not computing Green's operator of F, right? We are computing, it says right here, we're computing Green's operator of F perp. We're computing Green's operator of that thing. And remember, Green's operator doesn't go by the alphabet. It goes by first coordinate of the vector field and the second coordinate. So it's the x partial of the second coordinate minus the y partial of the first coordinate. Right? Thus giving us this result. And now it's just a matter of kind of simplifying, and these minus signs cancel. That's convenient. And what we end up with is this little thing right here, which we recognize. Oh my gosh, that's exactly the formula for divergence that we wrote down back in chapter 3 a long time ago. And so what we have all together, grand total, is that boundary flux can be computed as a double integral of divergence. So it's another one of these kind of weird theorems where something that's computed on a boundary is now instead going to be computed as a double integral over the interior, kind of like Green's theorem. no surprise that it's kind of like Green's theorem. Green's theorem was the sort of the big, thing that happened in the middle of the argument. Yeah.
So this seems to be around like flux around a boundary, but what if I just want to look at like a specific
flux through a
segment of
then this doesn't address that. This is specific to boundaries. Yeah, that's just kind of what we're interested in at the moment. Yeah. Right. Okay, so this is called the two-dimensional divergence theorem. There is a three-dimensional version of this that we will see soonish. The pace this class goes, maybe it's later this week. I can't quite remember. It depends on, I guess, our pace. But pretty soon, anyway, we'll be getting to that. Very handy fact. Let's see an example. Question says to compute the flux through the unit circle. Wait a minute. Outward through the unit circle. We want to compute this flux. Now, wait a second. Outwards through the unit circle. Unit circle. Let's think about the unit circle. The unit circle is like that. Let's see here. Let me be more careful. There's the unit circle. Is the unit circle a boundary? Why, yes, it is. The unit circle is a boundary of the unit disk. Right? Now, wait a second. It's tempting to say, so we've been asked to compute the flux through a boundary, but remember that word boundary is a loaded term. Boundary means oriented a specific way. We have to remind ourselves boundary means oriented outward. Have we been asked to compute the flux oriented outward? Why, yes, we have. Outward, indeed. So this is literally asking us to compute a boundary flux. Even though it didn't come right out and say that, that's what the thing we've been asked to compute is. It's a boundary flux. And once we make that realization, sweet. Boundary flux. The two-dimensional divergence theorem allows me to compute that as the double integral of divergence. And now it's a hop, skip, and a jump. We do have to compute the divergence, right? The divergence is this right here, because keep in mind, divergence says we're going to take the x partial of that, which is 2, and then plus the y partial of that, which is minus 5. And so the divergence very conveniently ends up being just minus 3. And so we just get minus 3 times the area, and we're done. And it works out super well. Everybody happy? All right. Okay, now I'm going to give you a different point of view on the result we just came up with, right? So we previously came up with this result here, the two-dimensional divergence theorem. We came up with it by basically kind of fiddling around with Green's theorem, right? Green's theorem is the one that we saw as an accumulation theorem. This 2D divergence theorem kind of came along for the ride as a kind of a tweak. If you look outward instead of along the curve, related notion and a couple of calculations. But we had not previously viewed this as being an accumulation theorem. But you know what? It turns out that it is. And you can totally take this point of view. It's a very reasonable point of view to just start off with the idea of boundary flux as being an accumulating quantity. I think this is a really worthwhile exercise. So let's ask the question with an open mind, is boundary flux an accumulating quantity? Okay, here's how we decide if boundary flux is an accumulating quantity. I need to look at the whole and compute boundary flux. Then I need to look at each of the parts that I would divide it up into and compute their boundary fluxes. and then C is the whole equal to the sum of the parts, right? So this is what it would mean to have an accumulating quantity. So let's draw the pictures now. What does the boundary flux of the whole look like? Well, there you go. Outward oriented boundary flux. Looks like that for the whole. What does outward oriented boundary flux look like for the left piece? Well, on the left piece of area, there's what outward oriented boundary flux looks like. And now on the right piece, here's what outward oriented boundary flux looks like. And I want to ask now, is green plus blue equal to purple? And it's tempting to say, close but not quite, right? But let's get rid of the stuff where they obviously agree. Here's the leftover. Here's the seeming difference, what you might call the impediment to accumulation, is the fact that there's these leftover terms here, but those leftover terms have opposite orientations and they cancel, and therefore, in fact, there is no difference, and the whole is the sum of the parts. So, how about that? Isn't that weird? And by the way, notice how very, very similar, and I laid it out on the page here on purpose to look just like the analogous argument that we made several pages back here, right? This edge appears twice with opposite orientations and then cancels. Right? Because it really is very, very similar. It's just that here we're talking about two different directions along this new edge. Whereas down here we're talking about two different directions through this new edge. But it's still opposite orientations on the new edge. Okay, so very, very analogous. Just real quick, here's a point of view on densities, accumulations and densities. Right now, the sort of chapter 5, extremely familiar, extremely unremarkable, point of view on this is with mass. And mass is obviously an accumulating quantity. The whole is the sum of the parts. Well, of course it is. If you could create more mass just by cutting a piece in half, right? That'd be a neat trick. But sadly, not so, right? The whole is the sum of the parts. Mass doesn't just disappear because you choose to view it as, a left side and a right side instead of a whole. And mass, being as it is a stuff distributed across area, there is an associated notion of density, which of course we call mass density, because the object in question is mass. Okay, that's all yawn old news. Now notice, and I write this down this way just for the sake of underscoring the analogy. Circulation and boundary flux are also accumulating quantities. Those are weird facts. Those are not obvious, but despite the fact they're not obvious, they're just as true, and therefore circulation and flux can be viewed as distributed across areas, just like mass is. And likewise, in the same way that little pieces of mass can be related to areas by way of a density, likewise, little pieces of circulation can be related to area by way of its circulation density that we talked about previously, right? Green's operator is circulation density. And likewise, little pieces of boundary flux we can view as being related to areas by way of flux density. So I think this is a really nice page here, really nice little comparison. I strongly encourage you to think about circulation density and flux density as being really highly analogous to mass density, right? And heads up, by the way, you will hear these terms used in just kind of, common, parlance I heard these terms a tremendous amount in physics classes, and I strongly suspect you're going to hear them in engineering classes as well. And so flux density in particular. In my experience in physics classes, I heard the term flux density more than I heard the term divergence. It's extremely common because it's extremely natural. It really makes a lot of sense. Okay. This term's a little bit less common, but it's certainly out there. Okay. Okay, so now I want to kind of switch gears and go back to the fundamental theorem of calculus. I know y'all know the fundamental theorem of calculus. My goal here is not to teach you the fundamental theorem of calculus. But I am going to take a weird point of view on the fundamental theorem of calculus for the purpose of making a comparison to the stuff that we've been talking about. And it turns out that among many other nice points of view, you can view the fundamental theorem of calculus as being an accumulation theorem, just like Green's theorem. We can view the fundamental theorem as being about the accumulation of a certain quantity with an associated density and thus computed with an integral. So let's walk through it. The accumulating quantity is what I call change. If you give me an interval, let me draw a little picture here. If you give me an interval on the x-axis from, let's say, x1 to x2, this formula right here, change, something that I associate to this interval, f at the end minus f at the start. You can see why we call this change. This is literally how much does this given function f, how much does it change over the course of that interval. And I claim that this is an accumulating quantity in the sense that if a function changes by a certain amount between x1 and x2, and then if it changes by another certain amount between x2 and x3, well then grand total gives me the total amount of change between x1 and x3, right? I think this is pretty believable, right? I mean, my favorite little silly analogy is if you were to keep track of, let's say my height as I was growing up, right? And say starting from when I was age 10, I guess it'd be about like this, right? Here was how tall I was at age 10. Here's how tall I was at age 20, right? So this change in my height, well, I mean, I could keep track of how much did my height change from 10 to 11, then how much did it change from 11 to 12, how much did it change from 12 to 13, etc. And each of those little changes contributes to a total amount of change overall. Right? The whole of the sum of the parts. Everybody buy it? All right. So, now we write down the fundamental theorem of calculus like this, that f of b minus, let me get into highlighter mode, f of b minus f of a is the integral of f prime, right? That's the good old, plain old fundamental theorem of calculus. Now let's take a point of view on this integrand. What can I say about this integrand f prime? And notice the role that it plays. Again, I have an accumulating quantity of change. And then I'm looking at a piece of change and relating how much the function changes to how much of an input change in x caused that output change. And let me draw that picture here, and let's imagine, let's see here, I'm going to zoom out just a notch here, and let's see, we will look at a little piece of this curve right there, and there's my output change, and there's my input change. So let's see here. There's dx. Here's my d delta. And so I can think of the derivative. Now, of course, classically we've thought of the derivative as being the slope. Rise over the run. And now all I'm doing is taking a different perspective on how to think about rise over the run here. Instead of thinking of this as rise, think of this as this accumulating quantity called change. And instead of thinking of this as a run or as a difference, think of it as a size. Right? So all together here, I've got change, accumulating quantity of change per unit size of a piece of the domain. So I've got stuff per unit size. Accumulating quantity, stuff per unit size, in this case length, but stuff per unit size is a density. So this, I know it's a weird point of view, but I think it's really, really nice for analogy purposes to think of the derivative as being change density. Everybody see that? And, this is not to knock the point of view of the derivative as being slope of the graph. That's also cool, right? Or a derivative tells you, the velocity of, your car as you drive along the road. Yeah, sure. That's all good. That's all fine in different contexts for different purposes. For what I want to do here, I think this point of view really nice. Okay, so one of the things I like about this is that this allows me to make a reasonable interpretation of this density. Because I can see the picture. Here's my picture. This is what's actually happening. And if I were to look at this overall picture and say, okay, well, for this entire interval, over the course of that entire interval, there was a grand total of that amount of change. That amount of change that I measure by looking at the starting value and the ending value. So I measure that change by looking at the endpoints. But now, just honest question. Where did the change actually happen? Well, the change didn't happen at the endpoints, right? Again, this is a modest observation. Change is measured at the endpoints, but that's not where it happened. I can see the function in the process of changing. Here's where it's changing. Right there, look, I can see the change in practice. So these points here, that's where the change actually happened. Those values of x. Right? And the derivative is what points to those values of x. The derivative is, let's see here, let me write it down. So the derivative here, where the change is actually happening, is big. A big value of the derivative is an indication that there is change happening at that point. This stuff, this accumulating stuff called change, has a high density at this point. And by contrast, over here, f prime is 0, and that's telling you that there's no change happening at those points. So the value of the derivative, let me say that differently, the value of the density, the relevant density, is literally telling you where in the domain that accumulating quantity is happening, right? So the accumulating quantity here is change, and here, where the density is high, is where the change actually happens. You buy it? Okay. Weird point of view. Just to get explicit about it. Let's look at this function here. F of x equals x squared, right? That's just a little parabola. And there's a certain amount of change that happens between 0 and 3. Okay, fine. Easy to compute the total amount that function changes. And f of 3 minus f of 0. Easy arithmetic. Okay, now I'm going to ask, though, where between the following 2 points, between 1 and 2, is there more of this total amount of change? Is more of it happening at x equals 1, or is more of it happening at x equals 2? And again, don't fall for the ridiculous line of, oh, well, the change happened at the endpoints. No, it didn't. The change was measured at the endpoints. The change obviously is happening over the course of the interior, right? All right, if the change is distributed across this interior, at which one of these is there more of it? Reasonable question. And again, the derivative just straight up answers that question. The derivative is our change density. I can compute the value of the derivative at x equals 1 and at x equals 2. And this is the one that's the biggest. And so 2 is where there is more change happening. And again, this tracks perfectly with what we see in the picture. Yes, there's more change happening at 2. It's steeper there. Right? Everybody buy it? Okay, so densities tell us where stuff is happening. And we can do the same thing with Green's operator. Now, this is, again, going to seem weird, but, we've talked previously about how circulation, it's something that we compute by moving along the boundary. That's kind of the definition of it, in fact. Excuse me. So circulation, we compute it on the boundary, we measure it on that boundary, but remember, I'm pushing this idea that that's not really where it's happening. That's just a measurement. Just like change isn't actually happening on the boundary. We measure change on the boundary, but change actually happens in the interior. You can literally see it for single variable functions. So likewise, circulation is actually distributed across the interior. And if you want to know where in the interior is there more circulation happening, Green's operator, the density, circulation density, is what tells us how much of it is happening where. And so in particular, let's see here, we can draw a little, if I were to, let's go to the little leaf. If I had a little leaf like that floating down the river, well, that little leaf is being pushed pretty equally on both sides. It's being pushed on its left and it's being pushed on its right, the same amount. I wouldn't expect this leaf to be rotating as it goes down the river. That leaf would probably just be translating, just kind of sliding right along. But if I were to look at this leaf here, that leaf is being pushed on its left, but it's being pushed harder on its right because the vector field's starting to get stronger. And so this leaf I would expect to be kind of rotating counterclockwise there. All right? And Green's operator is what's going to detect that. So what you're going to find for this vector field is that Green's operator would be positive there versus Green's operator would be 0 there. So the grand total circulation, where is the circulation actually happening? The circulation is actually happening in here, in that yellow region where you can see that the flow is kind of faster along sort of the bottom side, and so those leaves are going to be rotating. Everybody see it? Okay, and we're out of time. I'm sorry, I went a little bit over. We will pick up here next time, and see y'all later. Have a good one.